chi-square is a non-parametric test typically used when we have frequencies or count data. One of the benefits is that there's no need for homogeneity or normality. And we consider chi-square just as we did with the normal distribution to be a family of distributions determined by degrees of freedom. Here's an example of what chi-square looks like for k degrees of freedoms. We can see as chi-square increases from 1 to 9, it becomes less skewed in that chi-square starts at 0 and goes to positive infinity. But we can see with, for example, chi-square of 3, that light blue color, it has a little bit of a hump where it peaks around 1, whereas chi-square with 9 degrees of freedom seems to be peaking somewhere around 7. It starts to look a little bit more like the normal distribution as degrees of freedom increase, but it will always be truncated because its origin is 0. It does not go to negative infinity. The chi-square distribution is based on very much a simple premise: observed frequency minus expected frequency. So we see within the parentheses O minus E. So whatever we have observed minus what we would expect to be in that category. We square that value, divide by what we expected to see, and we sum our categories. Here's an example. So if we flipped a coin over and over and over again 100 times, we got 40 heads and 60 tails. Our expected value would be a 50-50 coin flip. We could use some of the basic principles of probability to come up with a 0.5 probability for that expected value. So when we calculate up the difference between observed minus expected, 40 minus 50 is negative 10. We square that value and get 100. We divide it by what we expected, which was 50. So 100 divided by 50 is 2. We do the same thing for tails and move across. I'll let you look at that yourself, but it's essentially the same math with positive 10. Now we have the value of 2 in the heads category, a value of 2 in the tails category, and we sum down those columns, or we sum across categories, and we get a chi-square value of 4. A dice roll example is very similar, just with more categories. What we would expect if we were to roll the dice 60 times. In this case, it is a 6-sided dice with values 1 through 6. If we were to roll this dice 60 times, and I said to you, how many times should the value 2 come up? You should be able to say, well, 1/6 of 60 is 10. So that's our expected value, and we can see what actually was rolled in a real example, values of 7, 13, 8, etc. We can do the same thing as we did in the heads and tails example. We can go across for 1 and see that the observed value was 7, the expected was 10, the difference is negative 3. We square that, we divide by what we expected, we get 0.9. We do that for all of our conditions 1 through 6, and then sum up the final column. We get our chi-square value. So for the one sample goodness of fit case, we are basically expecting those observed frequencies to be close to expected frequencies. What we observe should be what we expect. If it's different and large enough in value, then it's going to be significant. And just, if you want, in your back of whatever instructional stats textbook, or just Google chi-square online, and you can look this up just like you would your t-test or your z-test for a 0.05 or 0.01 level, given the degrees of freedom, which in this case, for the goodness of fit, are k minus 1. The standardized residual, or R, in this case, is the observed minus expected divided by the square root of E. It is an effect size that could be used for chi-square. It's not the only one, but it's the one we'll talk about right now in this video. For each category, if R is greater than 2, then we consider that category to be a major contributor. If you look at chi-square and R, you will get the idea that this is isolating a category. So we're not summing across all, we're just looking within each category. And instead of squaring the differences of observed minus expected, we are taking just the raw observed minus expected and then taking the square root of expected denominator. So in some ways you can think about this as some form of square root-ish type thing of the chi-square category. The test of independence is when we have two or more samples. So we will have two or more categories per sample, and there's independent and dependent data that could be used. So here we have an example of an independence test where we have two items on the test. We have item 1, we have item 2. Item 1, looking at the top, we have those that received a positive value and those that received a negative. And if we go down all the way to the bottom, we can see that 25 people received a positive, 25 people total received a negative. The same for item 2. We can look down the positives and the negatives and then go across the positive and see a 25, go across the negative and see the 25. What's in the middle portion is item 1 by item 2. So for those that received a positive for item 1 and received a positive value for item 2, that is, they both endorsed it or got it correct. There were 15 people in that category. We can see those that both got negatives also had 15s, whereas if you had item 1 negative and item 2 positive, it was 10, and the reverse is also 10. What we would expect to see, given the fact that item 1 and item 2 had a 50-50 split, 25 people out of 50 each got a positive and 25 people got a negative, we'd expect to see the interaction of 25 by 25 divided by 50, and essentially we'd expect to see that for each cell. So the actual expected value we could calculate here is 12.5. We can then go down the line like we did with our dice example or our coin flip example and say observed for the first category of positive and positive was 15. We expected to see a 12.5. The difference is 2.5. Square that difference, divide by expected value, and we get 0.5. We do this for each category, and we can get the observed chi-square of 2. So observed and expected as a second example. What we see in this example is our item 1. Outside of parentheses, we see actual values. And inside parentheses, we see the expected values. Here's the proportions for that previous example. So this is another way you could, if you wanted to, get your expected values. You could get the proportion within each cell first and then multiply it by the total frequency, the total number. I also show you this so as you go on for more advanced statistics or into educational measurement, this will be more helpful. The forms of hypothesis for our chi-square. The null is that the sample data are consistent with a stated distribution. The alternative is that the sample data are not consistent with a stated distribution. So for our goodness of fit model, we would say that we have a population value. We collect data. The population value is what we expected to have, expected to observe. And our collected sample is our observed values. We look to see if there's a difference. Our null says there will be no difference, or that the sample data will be consistent with what we expected to see, and our alternative says there will be a difference. For our independence test here, we have a null that says item 1 and 2 are independent. So our expected values that we calculate based on independence should be equal to our observed, and our alternative says they are not.